This is just a little bit more on separating mixtures for year 10, first booklet. If you want to look at anything extra, go to BBC Bite Size. It's under Key Stage 3 work, but it does explain different separating techniques of mixtures. And also, if you look at freesciencelessons.co.uk, there's a man that stands on one side of the screen, so you know you're on the right one, and he'll talk through separating mixtures as well, and he covers all the topics in GCSE as well. So he's useful to have a look at, and he does biology topics and physics topics. So filtering, make sure you know what the residue is. The residue is what stays in the filter paper. It's an insoluble solid. If it was a soluble solid, it would come through the filter paper. An insoluble solid is the residue. So for example, sand and water, chalk and water, if they were in the beaker, and you stirred them up, the sand doesn't dissolve, the chalk doesn't dissolve. So as you pour the mixture through the filter paper, the residue, the sand or the chalk would stay on the filter paper and the water would come through. Okay. Distillation. Distillation is where you have a mixture, say salt water or seawater. You've got salt dissolved in that. Now you can't filter that because the salt is dissolved. So you would distill it. And what would happen is, as it starts to boil, the water evaporates, comes through this condenser here, and you can see surrounding the condenser is cold water. And as the water vapour and the steam come through the condenser, here, so water vapour or steam comes through the condenser, it condenses, it cools down into pure water. Now whatever liquid comes out of distillation is called the distillate. It might not necessarily be pure water, it could be a different liquid, but it's the distillate. The salt will stay in the round bottom flask. You can see it's a round bottom flask because it's got a round bottom by the Bunsen flame. And also they might ask you about anti-bumping granules. Now you will put anti-bumping granules in there to cut down on the size of the bubbles, not to stop it boiling, but you don't make large bubbles then, which could cause the flask to rock back and forth. So you just make smaller bubbles. It boils more evenly throughout the liquid. Evaporation is another separation technique. It might also be called crystallization. Now, be careful on these diagrams. It looks as if you're boiling off all the water. We don't tend to do that. We just boil it to about a third of the liquid and then allow it to evaporate slowly because you make bigger crystals. So if you want to make salt crystals, you would allow the water, once you boiled it up and it started to evaporate, as it cools down, it evaporates more and there are bigger crystals forming. That's crystallization. You haven't kept the liquid here. You've lost the liquid, but you've kept the soluble solid. Fractional distillation. Now, fractional distillation is where you've got a mixture of liquids and they all have different boiling points. We know water boils at 100. If you have something called ethanol, which is alcohol, which is found in alcoholic drinks, that boils at around 75 degrees, 75 to 78 degrees. So it boils at a lower temperature. And what you've got here, as well as the condenser, you've got something called a fractionating unit or a fractionating column. And what that does, as the vapours go up the fractionating column, they just make sure that it separates out. There's no water coming over with the alcohol because alcohol will boil at a lower temperature, so it'll boil off first. And the water will stay in the round bottom flask. And once all the ethanols come off, then the water will boil off. Okay, so fractional distillation is where you've got a mixture of liquids with different boiling points. Another technique is using a separating funnel. Now what we've got here is something like oil and water. And you can see in the first picture there, the beaker, you've got a mixture of two immiscible liquids. Immiscible means they do not mix. and they've got different densities. So if you shake up water and oil, it'll turn into an emulsion. You'll see the oil mixed in with the water, and eventually it will settle down into 2 layers. Now you can see on the next diagram, the higher density liquid means it's heavier, so it will sink to the bottom, and the lower density liquid will stay on the top. And you put it into something called a separating funnel. You can see a little tap at the bottom. You open the tap once it's settled, once the 2 liquids have settled. You open the tap, you allow the higher density liquid to come through, and you close the tap and keep the other liquid in there. Okay, so if it was oil and water, the water now would be in the beaker at the bottom, and the oil would still be in the separating funnel. It's because they have different densities, and they also do not mix. Chromatography. So what we've got here is another different diagram, slightly different to what I've just shown you on the previous lesson. You've got your liquid at the bottom in the beaker. You've got your ink spot. Remember, the ink spot needs to be above the liquid, because if it was below the liquid, it would just wash away. And when it starts, the water or whatever liquid you're using, it could be acetone, it could be methylated spirit, the liquid rises up the paper, the chromatography paper, and the ink dissolves in the liquid. And the more soluble, or the more easily it dissolves, the further it moves. So if you look at the second diagram there, you can see that the black dot has now become grey, purple, blue, orange, red, yellow. Yellow is more soluble than blue because it's moved further up the paper. Okay? The ink spot there, if I go back, we tend to draw a pencil line to know where the ink spot needs to be drawn. And we draw the pencil line where to put the dot using pencil, because pencil doesn't dissolve in water. It's insoluble in water. So only the ink would move. If we drew the line in ink, the ink would wash away as well. You will need to know how to work out the RF value. RF value is how far a colour or a dot or a spot has moved. Now it's always the distance the dot has moved divided by the distance the solvent has moved. So that line is a dividing sign. So for example, the blue dot there has moved 8 centimetres. The liquid has moved 10. So your RF value for the blue dot will be 8 divided by 10, which is 0.8. The RF value for the purple dot's moved 6 centimetres. The solvent has moved 10. 6 divided by 10, 0.6. Okay? There are no units for RF values. I don't know if I accidentally said 0.8 and a unit then, but the RF value for the blue dot is 0.8, no units. The RF value for the purple dot is 0.6, no units. And the red dot is 0.2, the RF value. And remember, the RF values are always between 0 and 1, so you know you've gone wrong in the exam if you've got something above 1. The solvent front won't necessarily always move 10 centimetres, so you will put that number on the bottom, whatever they tell you to. You might have to measure it in the exam as well. But again, we look at some examples when we get back into class. Okay?